There are lots of ideas about what math is and why we learn it at school, and there are just as many emotional responses to learning math. By far, the most common response I get from people who learn that I'm a math teacher is that they're not very good at math and they didn't like it in school. Well, at least they perceive they're not very good at it. I think a lot of that has to do with the fact that math has very few concepts compared to a lot of other subjects, but there aren't as many entry points because those concepts are really deeply linked in a neural chain and a network of prerequisites. Students can perceive they're not good at math if they get lost, if they miss a day, if they fall behind for some reason, and then they never fill in those gaps. Sometimes they're not satisfied with the explanations they're given, and they lose interest, they're disengaged in the subject, and they get really frustrated, and then their apathy grows into distaste. I think it's really important that we fill the gaps in for students, but we also identify where some of these obstacles to future learning can come from. Where might they arise? A lot of students want to just memorize things as a result because they feel it's maybe a futile subject, something that they can't really grasp. And memorizing just to pass a test, just to kind of move on to something else, is really the status quo today, the way of math du jour. And if we could really bring it back to what math is, which is focusing on deduction and reasoning, which are really crucial skills in today's day and age, instead of just getting the right answer, which in light of Google and ChatGPT, we don't need to get the right answer so much as we need to process, to think for ourselves, and to figure out how to logically deduce something and to analyze. So while decision making and analysis are more important than ever, they're kind of taken out of the mainstream math classes. They're not really practiced. So I want to show an example of something where a really kind of innocuous approach to defining something or to referring to something can have some long-term effects. And this might be an example of something that causes students to be disengaged in mathematics and to feel like they're not a math person. Let's take a look at this for example. A common topic that students have in high school math is logarithms, whether it's numerically evaluating a logarithmic expression or analyzing functions, drawing their graphs, or using identities and properties to manipulate logarithms. And I think the reason that something like this is confusing for students is because of the confusion that we have in naming this expression here. 2 with a little 5 superscript equal to 32. Now, I don't think there's any dispute that this is called an exponent, but I think that there's a lot of confusion around the word power. So let's take a look at what the internet has to say. I typed in 2 to the 5, and I got a calculator giving me the answer of 32, and then some other questions that people asked. So I looked at this one. What does 2 to the power of 5 mean? So 2 to the power of 5 means 2 multiplied 5 times together. I would say that this is 5 copies of 2 multiplied together. And when we do that, we get an answer of 32. So 2 to the 5 is written as 2 to the power of 5. And here's another graphic. The 5 is called both an exponent or a power. The base is the 2, and the solution is the output or answer of 32. And then I looked up what is a power of a number in math, and I got the power or exponent, indicating that these are synonyms. It says how many times to use the number, meaning this number, which is the base. And it is written as a small number to the right, okay, indicating it's a superscript. And so I also typed in what is an exponent of a number in math, and I got the same thing. So this is really indicating the sense that these two words, power and exponent, are synonyms. So then I took a look at a variation 10 to the 2, and not only is the 2 called an exponent or a power, it's now also referred to as an index, and it refers to how many times to use the number in multiplication. So certainly we're going to come up with a problem if we have an exponent of 2.1, for example, because we can't multiply 10 2.1 times together. So I think the word index, we're just going to cross it off now and realize that index is only in the case that the exponent or the power is a positive whole integer. And this is an instructional video I found on YouTube. Here we're talking about exponents. We've got 10 to the 2, and it's written or said as 10 to the second power. So again, a sense that power and exponents are the same thing. This is just some textbook I found online, and it says the number of times you multiply the base is called the exponent or power. 5 is the exponent, and we would say 2 to the 5 out loud as 2 to the 5th power, or sometimes just 2 to the 5th. From here, I looked more for some text on the internet, and I found a tutoring website that talked about exponents and powers as being different things. Unfortunately, there's a bit of a typo here. This 3, 4 is meant to be 3 to the 4. So they're saying that 4 is the exponent when we have 3 times 3 times 3 times 3, and 3 is the base. But then it says that the whole expression 3 to the 4 is said to be power. So the power is the result of 3 to the 4. And just for reiteration, it says power is an expression that shows repeated multiplication of the same number or factor or base. And by contrast, the value of the exponent is the number of times the base or number or factor is multiplied to itself. So this is a slightly different definition from what we've seen before. But in this same website, there's a bit of confusion, because then it goes on to say, for example here, a to the n is called the nth power. In other words, a to the n is the power. And then it says that a is the base and n is the exponent or index, which is fine. We've decided not to use the word index, but it also uses power as a synonym for index. So that's in direct contrast to what it's saying here, that the power is the expression that shows the repeated multiplication and not just the number of times that the base is being multiplied. So what I want to establish here is the lack of clarity surrounding the words exponent and power, and how that leads to confusion for beginning students, or even students who haven't just learned exponents and powers and logarithms, but students who have been using these for a few years and then extending their learning into calculus and infinite series, for example. I then went over to Wikipedia and looked at the powers of 10. This, of course, is a very common topic since elementary and primary school when students are learning about the decimal system. So Wikipedia says that a power of 10 is any of the integer powers of the number 10. And I find this a bit confusing because it's a circular definition, but I went on to read. In other words, 10 multiplied by itself a certain number of times. So I'm taking that to say that a power of 10 is 10 multiplied by itself a certain number of times. And so I take that as the result of 10 multiplied by itself a certain number of times. It goes on to say that the number 1 is a power of 10. It's the 0 with power. And then the first few powers of 10 are 1, 10, 100, 10,000, and 10,000, etc. So this graphic over here is showing that the powers of 10 are the numbers 1, 10, 100, 1,000, 10,000, and so on, and not the numbers 0, 1, 2, 3, 4, 5. Now, I didn't highlight the word non-negative here because I find it confusing, because if you take 10 and you multiply it by itself, another 10, and you do that repeatedly, you will only get positive multiplied by positive, and that result will only be positive. So then needing to specify non-negative is unnecessary. And then I just looked at further down the website, and it comes up with a column of the words 1, 10, 100, 1,000, 10,000, which, if I recall, Wikipedia just called these the powers of 10. And in the next column, they have the column heading power, which is 0, 1, 2, 3, 4, 5. Now, I don't believe that these numbers were stated as the powers of 10. And over here, the heading is number, but again, these are just the digit notation for the powers of 10. So we're seeing that we've got different columns, different namings. Here, I would say that these are the exponents that we put on the base of 10. Exponent on 10 to get these powers. So this is slightly confusing and a bit circular. Later on, I saw that the sequence of powers of 10 can also be extended to negative powers. Again, when we consider that 10 is being multiplied by itself, 10 times 10 times 10, positive times positive times positive, and so on, can never be a negative number. So this is a little bit misleading, and again, we have the idea that power is the synonym for exponent here. Meanwhile, 1, 0.1, 0.01 are indeed powers of 10. So we're getting some confusion here because there are further contradictions here on the same website where 10 to the n is generally used to denote powers of 10. So those would be the numbers 1, 0.1, 0.01, or 1, 10, 100, 1,000, etc. Now, I'm not trying to prove something rigorously here. I'm simply pointing out the inconsistencies that a beginning student would have in understanding what an exponent or a power is, and then how that might lead to cracks in the foundation further down the line. So in light of this brief exploration, what number would most people say is the power in this equation? And I believe most people would say that the power is 5. So let's broach this from a different perspective. Let's take a look at grammar. Consider the ordered list of Kate's daughters from oldest to youngest. They are Anna, Bria, Chloe, Diane, and Eden. Who is the third daughter of Kate? Well, the third daughter in this list is Chloe. So as a sentence instead of a question, the third daughter of Kate is Chloe. The fifth daughter of Kate is Eden. And a slightly contrasted sentence, the fifth letter of the alphabet is E. So let's look at it from the perspective of a sequence, an ordered list of numbers. Consider the ordered list of the multiples of 10 starting at 10, the first multiple of 10. We have 10, 20, 30, 40, 50, and so on. Which is the third multiple of 10? So the third multiple of 10 is 30, and the fifth multiple of 10 is 50, and a different sequence, the fifth multiple of 2, we would start at 2 and add 2 to get this sequence known as the 2 times tables or the multiples of 2, and the fifth multiple of 2 is 10. Okay, last one, I promise. Consider the sequence of the powers of 10, starting at 10. So we're going to base this sequence on 10 by starting at 10 and multiplying by 10 to generate successive powers of 10. So we have the first power, the second power, the third power, the fourth power, the fifth power of 10. And so the third power of 10 is 1,000. The fifth power of 10 is 100,000. And the fifth power of 2 would require coming up with the power of 2 sequence. So we base the sequence on 2 by starting at 2 and then multiplying by 2. And we come up with, here's the fifth power of 2, 32, and we can keep going beyond that. So the fifth power of 2, first, second, third, fourth, fifth, is the number 32. So in the equation 2 to the 5 equals 32, what number is the power? Well, this is the confusion because most people would say 5 is the power, but we've just said that the power is 32. And so what we're really facing here is an issue of grammar. We wouldn't say that the fifth power of 2 is 5 because 5 is not even in that list. We wouldn't say that the third power of 10 is 3 because 3 isn't in the list of the powers of 2. Similarly, with Kate's daughters, we wouldn't say that the third daughter of Kate is 3 because 3 is not one of the daughters of Kate. Or for the multiples of 10, we wouldn't say that the third multiple of 10 is 3 because 3 is not in that list of the multiples of 10. So when we're looking for the daughters of Kate or the multiples of 10 or the powers of 10, we're actually looking for the output of a function and not the index input. This is the crux of the problem that students have because, well, we say this is an index, but when we extend these natural numbers to the real numbers, we've decided to call those exponents. And so that input of exponent can't take on the same name as the output, but when we use the word power as a synonym for exponent, this is causing an input-output clash. And students get really confused at this level, but certainly when we come up with the inverse of an exponential function, which is a logarithmic function. So how do we alleviate this? What could we do to make it clearer and prevent any obstruction to future learning? Okay, let's recap some of the different ways we saw to read 2 to the 5 equals 32. The fifth power of 2 is 32. We also saw 2 raised to the fifth power is 32, or 2 to the 5 is pronounced as 2 raised to the, or you could just eliminate the word raised and say 2 to the exponent, or 2 to the power 5. 2 to the 5, which is a bit more ambiguous. I guess it doesn't specify the word exponent or power. 2 to the fifth power, and 2 to the fifth. These are some of the different ways that we've seen. And it's coming up with the idea that the base is 2, the exponent is 5. These aren't really disputed. And that the power is 5 or 32. So I would like to submit that we don't call the power 5, and we call it uniquely the 32, the output of this exponentiation. So from that point of view, we have a base raised to an exponent equals a power. And we can say base to the exponent equals the power. So over here, let's just take a look at some of the different naming structures that we have. If we have something like x squared, the base would be x, the exponent would be 2, and the power would be the unit of x times x, or x squared. Similarly, in 2 to the x, the base is 2, the exponent is now x, so the x and the 2 have changed roles, and the power is still the unit, but this time it's 2 to the x instead of x to the 2. So for my first example of where a student might encounter the word power in a misleading way is looking at power functions versus exponential functions. A parent power function, y equal x to the n, and the parent exponential function, y equals b to the x, both have a base, an exponent, and a power. Y, the output, is a power in both cases because we have a base raised to an exponent. But in this case, the input variable x is in the base for power functions, and the exponent is the constant m. But for an exponential function, the base is the constant, and the exponent is the input variable x. Being able to compare and contrast different families of functions is a really important skill in analyzing functions, because once you can make some comparisons, you can draw on prior knowledge, and then when you contrast, you can extend that prior knowledge into a new territory. So one of the things we might contrast about power and exponential functions is the end behavior. So we're going to focus a little bit more on the exponential functions, except to say that the form of the parent functions can be extended to look like y equals a times x to the n for the power function, and y equals a times b to the x for the exponential function. And of course, we've got some domain restrictions and some conditions on the parameters. Okay, so let's take a look at kind of a clarifying question. What is the power in the expression e squared? There's going to be a lot of old myelinated neural nets around this idea, and people will want to say 2. But if we think of the base raised to the exponent as the unit of the power, then the power is actually e squared. And now we can ask a question that is not as familiar as what is the exponent that we put on base 2 to get 32? We know this number, we know the exponent is 5, but rather what is the exponent that goes on a base of 2 to get the power of 10? And now, of course, we're looking to undo exponentiation with the base of 2 to solve for the exponent. And for that, we need logarithms. But first, let's see how distinguishing the terms exponent and power can actually give a student insight into logarithms before formally introducing them. We're looking for an exponent that we put on the base 2. So we're looking at the powers of 2 sequence. And the specific power that we're looking for is 10. It's worth taking a moment now to say that the word power is actually a mistranslation of the word amplify or amplification. So by taking a base number like 2 and repeatedly multiplying by itself, we end up amplifying that number to get the powers 2, 4, 8, 16, 32, and so on. So when we pull up our powers of 2 sequence, or at least the perfect powers of 2, for which the exponents are actually indices, whole numbers, we notice that 10 is not part of that sequence of the perfect powers of 2. So we place 10 in between the perfect powers of 2, which are 8 and 16, and knowing that as the exponents increase, the powers increase, we're looking for some exponent that lies between 3 and 4. So this is a really good numerical intuition way that leads us to introduce logarithms. So in order to understand logarithms, let's really extend our first language, the language of exponential functions, and let's complete a table of values for a set of given exponents for the y equals 2 to the x function, the exponentiation base 2 function. We knew our sequence was 2, 4, 8, 16, and so on over here. We see the doubling pattern and going in reverse by one block in the table, which is decreasing the exponent by 1. We take 1/2, we multiply by 1/2. So this is really helpful because it allows us to see the pattern between changing the sign of the exponent and reciprocating the power. So having this language is really clear when we're starting to work with more abstract notation. And let's write those words in here. This is exponents and this is powers. Okay, So we've got a relationship here between changing the sign of the exponent and reciprocating the power, and now we really want to work backwards. If we know the base of 2 and we know the power, what's the exponent? Well, the naming system of base raised to exponent equal to power is really nice because there is one unique exponent for each base that leads to a power, and this mirrors the one-to-one nature of an exponential function. So if we're dealing with a base of 2 and the power is 8, the exponent we're looking for is 3. Similarly, if the power is 16, we are looking for an exponent of 4. A power of 1/8, which is the reciprocal of the power 8, we have the negative of the previous exponent of 3 to get -3. If the power is 1, the exponent we are looking for is 0. Now this is a case that's really confusing for students, so clarity with the words exponent and power is really, really helpful. The exponent we're looking for to put on base 2 to get the power 1024 is 10. If we extended the pattern and had some familiarity with this set of numbers, that would be really helpful. And the power that's the perfect power before 1024 is 512, and so the exponent is 9, and then the reciprocal of 1 over 512 has an exponent of -9. We want to find the exponent on the base of 2 to get the power of 0. And we notice that if we keep going forwards into the right of this table, our powers get bigger, they double. And if we go to the left, our powers halve. And so we are taking, if you consider starting at 2 or 1, it doesn't matter. These are positive numbers. Taking half of a positive, positive times positive times positive times positive times positive, will always be positive. And so we get a really important statement, and that's that powers must be positive. And that's telling us that as the exponents keep going to the left, approaching negative infinity, the powers will approach smaller and smaller positive values, so they approach 0. And in this way we see that powers will never be 0, and they will also never be negative. So I'm just going to write undefined in here, even though we can unpack that a little bit further, because one undefined is a type of infinity, and the other undefined is a complex number, non-real value. Okay, so we've got our beginning numerical sense of working backwards from the power to get the exponent. So what we really want to do is come up with a shorthand for that statement. And so the exponent on base b that yields the power p is read as log base b of p. So we can see that b is the base, p is the power, and the entire expression represents the exponent. So getting students to say this over and over again is actually really, really helpful because it's myelinating the neural nets in the brain so that we are replacing the old understanding that the power and the exponent are the same thing. So log base b of p is just a mathematical shorthand that says this expression is the exponent on the base of b that yields the power of p. Now, I don't really like this wording anymore. We could say this is the exponent associated with a base of b and a power of p. That might be easier. Anyway, log base 2 of 8 is the exponent on the base of 2 that produces the power of 8, and that exponent is equal to 3. So we could just get students to do a bunch of these. We have a base of 2, a power of 16, and the value of that exponent is 4. Log base 2 of 1024 is the exponent on the base of 2 that yields the power of 1024 and is equal to 10. And log base 2 of 1 over 1024, the base is 2, the power is the reciprocal of 1024, and when we reciprocate the power, we negate the exponent. Changing the sign of the exponent reciprocates the power, and vice versa. So once we have a little bit of facility with the abstract notation, we can play more with tables of values so that we can come up with a graph and start to analyze more behavior of the function. So in this particular case, I haven't given any of the values here, and it's up to us to kind of remember what these things represent. So in this case, 2 represents the base, and x represents the power. So we might want to write that in a little bit just to kind of give us a reminder. And then the output over here, which we could also call y, is the exponent. So another way that we could write this is to say 2 to the exponent y is equal to the power x. And so this is familiar to us, and it's equivalent, although we're isolating someone different. Over here, we're isolating the exponent, and here we're isolating the power. X still represents the power, even though it's isolated over here. So I want to come up with different values for the exponent. I'm actually just going to write the word in here again. We've got power and we've got exponent. So that's helpful to remember. Now I might put a 0 exponent here, and as I did before, just increase my exponents by 1 and decrease them by 1 on the other side. Now I'm not going to fill all of these in, but just to get a sense of how I might approach this with students, then we know what the powers are because we just did it in a previous table of values over here. All we're doing is putting the powers first, which is coming up with the powers as the input. But I'm used to thinking of the exponents, so I'll just come up with a few of these powers, and we'll move on from here. Okay, so we come up with some families of functions. These are the exponential growth functions and the logarithmic growth functions associated with them. This blue one is y equals 2 to the x. And what I might have students do at first in this parent function is to represent x here and just remind us that x is the exponent. And over here, y is the power. And then here we have swapped the roles of the input and the output. So y represents the exponent now, and x represents the power. And so if we had, let's say, an ordered pair here, I don't like that one, let's take 3, 8. The exponent is 3 when the power is 8 associated with the base of 2, or 8, 3. We're just swapping the input and the output. The discussion about exponential and logarithmic functions being inverses of each other might prompt a student to wonder what the inverse of a power function is. So if we consider our power functions had the form y equals a times x to the k, we notice that we had the variable x in the base versus the exponential function where the variable x is in the exponent. And so we really want to figure out what's going on with the inverses of these functions. So let's just take a parent function. Let's choose a equal to 1. And well, k is not just an odd or an even whole number. We might look at k being some real number. So let's take a look at some various values of k. So in this case, k is equal to pi, and so we have x to the pi, or the inverse, x equals y to the pi. So here we have functions that don't have a domain of all real numbers, and if we let k equal to the whole number 3, we see that the domain for both the blue function and its inverse, the red function, does have a domain of all real numbers. We can take a look at k equal to 2, and we see that the inverse of this function, the blue function, is not a function. So we have problems with one-to-oneness here. But that doesn't just happen for the whole numbers. We can see for fractions like 2/3 for k, we have some problems with the inverse being a function. So there needs to be some kind of restricting of the domain of the original function, let's say the blue one, before we find the inverse. So for now, let's just consider the cases of k being a whole number, the odd numbers and the even numbers, and that gives us two families of power functions. Generally speaking, if we want to get the inverse of a function, we want to undo what's being done to it. So undoing the caret k, we could raise both sides of that equation, that function, to the reciprocal exponent, 1 over k. And so we would get y to the 1 over k is equal to x. So the inverse function is taking whatever the base is and raising it to 1 over k. So if the inverse function is being applied to x, this would be x raised to the 1 over k. So this doesn't have a name unless k is a special number. Now if k is a whole number, a non-zero whole number, in fact 2, 3, now I'm using n. If it's 2, 3 or greater, then we would call these functions the root functions. This explanation about the inverses does lead to a discussion about restricting the domain for those power functions that have even symmetry, the ones that turn around. But it also leads us to recall the exponent laws. In particular, for coming up with the root function, we see the exponential to radical notation of fractional exponents leads to an nth root, where n is a whole number, not equal to 1. But now this draws my attention to the other exponent laws, namely things like x to the a times x to the b is equal to x to the a plus b. In this updated notation of power, we see that we have powers of x to the a and x to the b that are joined in multiplication. So we're multiplying two powers that have the same base. And in order to condense that, we keep the base and we add the exponents. Again, clarifying the terms power and exponent really helps students to understand. But it also gives us more insight when we look at the same law from the perspective of a logarithm. Keep in mind that in the exponential notation, base raised to an exponent, we are isolating powers. But in the logarithmic expression, we are using an inverse notation, so we are isolating exponents. Let's see the same law. Let's take a look at this one here. This is the log of a product, which is the sum of logarithms. Now look at the understanding we gain if we really reinforce the terminology. This says log base b, so this is the base, and we take logarithms of powers. So u times v is a power, and here we're multiplying two powers. And now the base with this power has an associated exponent, which is this entire expression. So here we have an exponent, and on the right-hand side we are adding two exponents. And so we see that when we add two exponents, we condense or expand by multiplying two powers. Both laws say that when we are multiplying powers that have the same base, we add the exponents. The two laws say the same story, but from different perspectives. In exponent laws, powers are isolated, and in logarithm laws, exponents are isolated. Once we have a good verbal and numerical understanding in mathematics, we go along and build higher levels of abstraction, and we move on to graphical and analytical or algebraic approaches. So we're going to analyze some logarithmic functions, and we do that by building it from prior knowledge. So we will link the exponential function and its inverse logarithmic function. So let's just look at some of these things, domain and range of each of these functions. The domain of an exponential function is the set of x values, and those x values represent the exponents. So I might put that here just for clarity, and meanwhile y is the set of powers, specifically the powers of 2, because our parent function is the exponentiation base 2 function. And there are no restrictions on exponents, so we have that the domain is x is contained in the reals. Meanwhile, we know that powers must be positive because we are repeatedly multiplying 2 by itself, well, at least as far as x being a whole number is concerned, and positive times positive repeatedly is only ever positive. Meanwhile, in the inverse case, we've swapped the input and the output, so x now represents the set of the powers of 2, and y is the set of exponents. Again, there are no restrictions on exponents, so y, the exponent, can be anything, and x, the set of powers, must be positive. We also get an asymptote whenever the power approaches 0, and we see that that's a horizontal asymptote in the case of the exponential function, a type of end behavior, and it's a vertical asymptote in the case of the log graph, which is a type of discontinuity. So we then come up with this domain condition that we can use in all sorts of application problems. So here's a question, for example, to determine the domain of this function, and if we really analyze it, we see that y must be the exponent as the output of a logarithm, e is the base, and the expression x squared minus x minus 6 is the power. And so understanding that powers must be positive, we see x squared minus x minus 6 greater than 0, and then we can go ahead and solve this in a couple of different ways. I might solve it graphically, comparing two graphs, and if I sketched a graph of the parabola and the horizontal axis, y equals 0, and something like this for my parabola. I'm looking and seeing that I want the red graph to be purely higher than the blue graph, which leads us to regions to the left of x equals negative 2 or to the right of x equals 3. So the domain would be x is less than negative 2 or x is greater than 3. Then if we were to go ahead and take a look at the graph of this function, we can confirm that domain. And indeed, at x equal to, I think it was negative 2, x equal to 3, we had a couple of vertical asymptotes, which were those places where the power is attempting to be equal to 0. And so we have the domain in two regions. So we can analyze and understand a lot more about logarithmic functions because we understand the base exponent power even better. Since exponential functions have y-intercepts when x is 0 and horizontal asymptotes when the power approaches 0, we can use that information for the inverse case. So the log functions have x-intercepts when y is equal to 0 and a vertical asymptote still when the power approaches 0. Now we can take a look at this transformation of a log function and rewrite it in a form that allows us to identify the base, the exponent, and the power. This form is the transformational form. From here we can write it in exponential form where we have the y in the exponent and the x in the power. Then we identify the transformations as a vertical reflection, vertical translation of 1, and a horizontal translation of 2. If we apply these transformations to the parent function, it could be expressed either as a function of y or as a function of x, and then we can use this information to come up with the x-intercept and the vertical asymptote. We can use the transformations on the parent function to sketch the transformed graph, or in the case of a one-to-one function like this log function, a table of values is just as easy. I'm using the y values to figure out the x values, and from there we can come up with a set of points that help us to sketch the graph, and then we can state the domain and the range. Okay, let's move beyond pre-calculus and analyzing basic functions to consider how learning terminology of exponent versus power differently could impact a student in calculus. One of the first things a student learns is the derivative of a power function. But with the idea of power being synonymous with the exponent, we don't really get the sense that the power function is the base raised to the exponent, where the exponent is constant and the base is variable. So that when students take the derivative of exponential functions, they try to take the derivative in the same way. We would use the limit definition of the derivative to come up with the derivative for e to the x, and then use that to find the derivative of 5 to the x. To do that, we need to change the base. For example, we would change the base 8 into a base of 2 by writing 8 as a power of 2. So we would need to find an exponent on the base of 2 that gives us the power 8, and that's 3. So in the case of 9, if we wanted to change 9 as a power of 2, we would need to find an exponent that we put on the base of 2 that gives us the power 9. And this is our verbal definition of logarithm. Log base 2 of 9 is the exponent that we put on base 2 to get the power 9. Now we do the same thing to change the base 5 into base e. We find an exponent that we put on base e to get the power 5. Using our logarithmic definition, we get log base e of 5. And then log base e is the natural logarithm, so we write 5 equals e to the ln, or ln of 5. From here, it's a straightforward exercise to find the derivative of 5 to the x using the derivative of e to the x in conjunction with the chain rule. The change of base approach is used to find the derivative of all exponential functions. To take the derivative of a logarithmic form, we want to be really clear on the role of exponent and power. So we write ln x and exponent as y, and then identify the base e, the power x, and the exponent y, so we can rewrite in exponential form. E to the y equals x. Now we can use the derivative of exponential functions in combination with implicit differentiation to get the derivative of y. So we get e to the y times the derivative of y prime, which is equal to 1, and solving for y prime gives us 1 over e to the y, and substituting back e to the y as x, we get the derivative is 1 over x. So this is our basic logarithmic derivative, and from here we can use change of base to find all other logarithm function derivatives. One last place I want to show that the word power comes up is in power series. We often talk about infinite power series, but we can also talk about power series as being finite and representing polynomials, for example. So here we have a cubic polynomial approximation to e to the x. When we get to the terms series and infinite, it can be a heavy load for students, so making sure that the word power is really clear can go a long way in understanding the new concept. So remembering that a power function is a function of the form a coefficient times x to the k, students can start to see that each of these terms is a power function, and then by adding them together we're getting the series. So here is just a cubic polynomial approximation to e to the x. It's Maclaurin or Taylor series approximation. And here is 4 terms, a 7th degree approximation to sine x. Coming up with the pattern becomes a lot easier when the cognitive load is diminished because we understand what we're talking about. The mathematics and the applications I've presented here, well, they're not groundbreaking. But what I have done is asked us to use logic and reasoning, the hallmarks of mathematics, to question the status quo. Is the power the same as the exponent? I submit to you that it's not. And if we use those terms with more clarity, we can grant more access to mathematics for more people, creating more confident learners and learners who enjoy math a lot more. And to me, that's a very worthwhile endeavor.